So anyways, so if you recollect, we computed the small signal gain of this fellow by finding the short circuit GM and RO, right? And that's because we noted that the circuit was asymmetric. So doing common mode and differential mode calculations might not simplify my circuit. That was the logic. But we also made another observation that although this is asymmetric, is there some conditions in which it becomes symmetric? So for common mode, at least this will become symmetric. We can reduce the circuit, right? So let's try to do that way, because I know at least for common mode signals there is symmetry in the circuit. I should be able to do some simplified calculation. We don't know what will happen in differential mode, that we will see after this. So I'll take the same thing. Now I'm trying to compute the small signal gain by decomposing my small signal voltages V1, V2 as a common mode part and a differential mode part. So in terms of V1, V2, what was the common mode? V1 plus, it is essentially the average, right? Common mode is a fancy term for average, and differential is essentially the difference between the two. So that's how we are defining. So let's assume that I have an ideal current source to start with. Let's make it simple. I am now assuming that I have a common mode input applied to both sides. So which means along with the bias voltage, I have a common mode input added. So again, let's me write this is common mode gain. So we already know this circuit is now having a common mode excitation, same gate to source voltage. So then what can you comment about the two drain voltages? They'll be equal. So which means if they are equal, without telling anyone, I can go and short this silently. No one will know what happened. Things will remain the same. So which means now we can see the circuit can be reduced, because now these two fellows are put in parallel. These two are also put in parallel. So now I can draw the simplified circuit. So if I simplify this, this is VDD. I'll say this is 2x of M4 because two of them are put in parallel. Here I have, I'll say 2x of M2, and here I have VB plus VIC, and here I have the current source. Again, please note that what we are doing right now, it is not just valid for small signals. Even for large signal picture you can do this, because we are only relying on the fact that for symmetrical excitation the corresponding node voltages on the two sides are equal, so I can short it. So even for large signals I can do like this. Okay. Now you tell me, this is my V out. So if there is a small signal change in the gate voltage, how much will be the small signal change in the drain voltage here? There is a bias voltage. On top of the bias voltage, I am applying a small change in the gate voltage. How much will the drain voltage change by? Remain constant. Why? Yeah, again, the current flowing through the transistor is how much? Will it change if I change the gate voltage? So if the current flowing through the transistor is same, the PMOS will have the same VGS, correct? So which means this voltage will remain the same. So what is the small signal V out now? Is it clear? So I'll say the common mode gain is here is 0. Is the argument clear? As long as I have an ideal current source making the current to be constant, none of the voltages here will change, even though you change this voltage. But what will change in the circuit to keep the current constant? Yeah, this source voltage, let us say for it was earlier, let us say some Vs. If I increase the gate by VIC, this will also increase by VIC. That's the only change that will happen. Okay, so here why is the what element here is making the common mode gain to be 0? The ideal current source. Yeah, current source is what making it making this change to be 0. So let's make it interesting and assume that the current source is not ideal. So let me take it to next page. So now I'll assume that I no longer have an ideal current source. Let us say the current source has some output resistance Rx.
So you said the small signal output is 0
Correct.
because of the I naught current.
Yeah, because the current is constant here. Yes.
But I naught current is a DC current.
Yeah, I mean the circuit I'm drawing is also, it's a complete circuit, right? It is not for DC or small signals or AC. I mean the DC bias is here. On top of it, I'm applying a small change. I mean, irrespective of that, this circuit holds. I mean, this is the actual circuit, right? The bias voltage is there and the small signal is also there. So here itself, we made an observation that these two potentials will be equal. So I can short it. So this is the simplified circuit.
Because the current throughout is constant.
Yeah, that's all. Now let us say the current source has an output resistance. Now we can't make that argument because now let us say you are saying that the current is going to be same because the source voltage also increases by VIC. But now you see that there is a current flowing through Rx, so which means the current will not be constant, right? So we can't make that argument now.
So the short circuit part also not valid.
Which one? No, the short circuit, I mean, you are saying this one.
Yeah.
That is still valid, right? See, even if I have an Rx here, doesn't matter, right? All that we are saying is you can argue by the same thing. We, for the DC operating point, the same way we argued, we can now argue the same way. You can assume that, let us say the drain voltage here V3, you can assume that V3 is greater than V4. Then you will find that NMOS current will be great. I mean, this NMOS current left side will be greater than the NMOS current on the right side. But for PMOS, it will mean that current on the left side is smaller than the current on the right side. You will still have a contradiction. This argument that the two drain voltages are equal doesn't depend on the fact that the current source is ideal or non-ideal. Okay.
In previous cases, for small signal calculation, we are just making AC ground to the current source. So for these calculation, why we didn't make these assumptions?
No, why we never made this to be ground? There is a particular condition in which we made it.
So for the differential.
Yeah, but what are we considering now? We are applying a what kind of excitation? Differential or common mode? So here we have to compute, I mean here the output will not be exactly 0. Let's compute how will that be. So let's draw the small signal equivalent. So for small signal, the current source is open. I'll take it out. I'll only consider the small signal voltage VIC. The supply is again short. So let me draw Rx here itself. Okay. So this is my effective small signal picture. So again, let's not try to use KCL. Let's try to solve it from results that we already know. So again, this for small signals, this is a linear circuit or a non-linear circuit? Linear circuit. So I can always find the output voltage as my short circuit GM times R out. Correct. So let's try that. So let's find the short circuit GM first. So for finding short circuit GM, I am going to short my output. So let us say this is shorted, and I am interested to find this current. I will call it ISC. Now again, for small signals, the transistor I will treat it as a voltage controlled current source in parallel with an output resistance. Now remember, I have two transistors put in parallel. So what will be the effective value of this resistance here? Earlier for a single transistor it was R02, now it will become R02 by 2. Similarly, earlier I would have had just one current source whose current depended on GM. Now I have two current sources put in parallel. What is effective GM? I'll just write it as 2 GM. I'll not write VGS here. Assume that it's there. So now if I say that this current is my short circuit current ISC, what can you say about this current? Same or something slight difference is there? Can you look very carefully? I mean, is it equal to ISC or something else? Is it correct? And is it okay? It's minus time negative of the current. Right? So here I am considering the current flowing this way. So this current is going to be negative of that. So which means what can you say about this current? That is also minus ISC. Okay. So if I find, let us say if I call this Vx, so which means my Vx is minus ISC times Rx, or to find ISC I can say it's minus Vx by Rx. So my problem now boils down to finding this source voltage. The moment I know the source voltage, I can find the short circuit current. Right? So let's see how we can do that. Maybe I'll copy paste this. So now for short circuit calculation, look at R02 by 2. One end of this resistor is connected to this node Vx, other end is connected to ground. So I can say that this is going to come in parallel to okay. Or I'll actually show it explicitly so that, or I'll write it here. Hold on. This is R02 by 2, okay, and this is what is Vx. Right. Now I'll remove the GM. I assume that it is all there inside. We'll not draw this. So now look at the circuit. I have input applied at the gate. Drain is small signal ground. I am tapping the output from the source. What kind of configuration this reminds you of? Common drain. So again, if I have something like this where I apply V in here and I have a resistor Rs, what is my V out? Yeah, it was Gm times Rs by 1 plus Gm times Rs. So again this so which means here my effective Rs is this. So now we can directly write what is Vx. So what is Vx now? Yeah, VIC times. Remember I have 2 times GM here, correct? So it is GM times the resistance at the bottom by 1 plus that same factor. So this will be 2 times GM2 times what is effective resistance? Rx parallel R02 by 2 by 1 plus same thing. Okay. I mean, one thing to remember is this result assumes that R0 is infinity, right? So here I have included R0 here, so it is fine. Okay. If R0 is also there here, this is going to become Rs parallel R0. So that Rs parallel R0 is already included here. Yeah, that is what I am saying is, if I were to write it neatly, this is Rs and this is Vi. With including R0, this V out will be Gm times Rs parallel R0 by 1 plus Gm times Rs parallel R0. That's what you have written here also. So cool, this is now your Vx. So now I can directly find my short circuit current. which is Vx by Rx. So let me take it to next page. But till now what we have done is it okay? Let me know if there is any confusions. I mean, this is the only result I'm using. This is a good result to remember because I mean every time you don't have to compute what is the output here, right? So then what I'll do, I'll push this up here. So which means I can directly write my short circuit current as minus this term. I mean I'll directly write it. My short circuit current is negative of this by Rx. That's all. No need to write the complete expression, it is not needed. So let me just keep it like this. So this is my short circuit current. So what is the next thing I have to find? R out. So let's do that. R out should be simpler. So let me draw this again. This is Rx. I am trying to find the output resistance looking here. And when I am doing it, what will I do to my small signal input? Yeah, I'll ground it. So now, can you tell me, this is, I'll write it 2x of M4. This is 2x of M2. So can you tell me what is the resistance looking up here? 1 by GM or something else? I mean, if I have one transistor, it is 1 by GM. I have two of them put in parallel. It is 2 by GM or 1 by 2 GM? With one transistor, it is 1 by GM. Two of them in parallel, it becomes half. What is the resistance looking down similarly? I mean, what configuration it reminds you of now? The cascode configuration. So tell me the exact result for cascode. It is the resistance you have at the bottom plus it is the R0 of the transistor, which is half of the original R0, plus I have the intrinsic gain. My GM is 2 times GM. R0 is R0 2 by 2 times Rx. This is my looking down resistance. Okay. So I mean now you see looking up I have 1 by 2 GM. Looking down I have GM R0 times Rx. So what will dominate finally? So my R out is approximately I mean looking up I have a resistance of the order of 1 by GM. Looking down I have some GM R0 times Rx. So looking down it's going to be a larger resistance. Should not be surprising. Cascode we used to make a better current source. So the output resistance should be much larger. So the looking down resistance is much larger than the looking up resistance. So the overall resistance is approximately 1 by 2 GM4. Is it clear? So now I can write my output directly. My output voltage is a short circuit current times R out. So I'll just write it for the sake of completeness. It's not very critical. So this is my short circuit current times R out. I'll just multiply it by 1 by G. Correct. That's all. This is what we will try to do calculations. I mean, see, this is already a big expression, right? If you were to use KCL and solve it, this would actually be really lengthy. You might not get any intuition from the calculation. But if you break it down into smaller portions and use results that you already know and simplify the circuit, it becomes more intuitive, and with practice, I mean, if you are experienced, you might not even draw all this. By inspection, you will be able to write this directly. Oops. Yeah. So this is what we'll try to do in the course. Hopefully, in the course of time, you will also get comfortable with this. But whatever I did now, is it clear? If you're able, tell me if you are able to follow my thought process and my logic. That's all. So the only result we used here was the common drain result and the output resistance of a cascode and some few impedances. If you have diode connected device, what is the output resistance and few. If you remember those tidbits here and there, you should be able to write it directly. Okay, so now I have gotten this big expression. Let's see if it makes sense, or if this is correct, right? So is there some sanity check I can do, or no sanity check, I mean, is there some quick check I can do so that to see if my expression is correct? Yeah, I mean, we already know if Rx was infinity, what is V out? 0. That is something we already found out, right? If Rx was infinity, V out was 0. So that we can quickly check. If I tend Rx to infinity, does it become 0? Yeah, because I have Rx in the denominator. You make it infinity, it becomes 0. Yeah?
One Rx in numerator.
Yeah, but Rx goes to infinity, this goes off, right? This is Gm times R0 by 2. Great. So the common mode gain at least we computed. Let's also try to do the differential mode gain. Let me copy paste this. So now I'm trying to find the differential mode gain. So my inputs are, I will say, plus VID by 2 and minus VID by 2, so that the differential is VID. And for this calculation, I'll assume that we have an ideal current source, because we already know the circuit is asymmetric. So I don't want to introduce additional complications by assuming non-ideal current source. Let's start with this. So let me ask you this question. If let us say I didn't have this connection, how would you simplify the circuit? Huh? Yeah, how will this become half circuit now? Yeah, remember, if I have two, for small signals, this is a linear circuit. If I have two symmetric circuits with anti-symmetric excitation, we already saw all the nodes along this line of symmetry. That will be 0. So which means we can argue that Vx becomes 0, same as this. So this reduces to a half circuit like this. This is the half circuit. But unfortunately, you can't make that statement now, because this is not a symmetric circuit. We have this asymmetry. Now tell me, in this circuit, the symmetry is at the drain side of the NMOS transistors or at the source side of the NMOS transistor? Asymmetry. The asymmetry is at the drain side or the source side? Drain side, right? And so let us say I consider a case where I ignore the R0 of the NMOS transistors. Let us say I make this for simplicity. If R0 of the NMOS is infinity, then remember R0 is connected from drain to source. Of course, you also have the current source, but the value of the current source itself doesn't depend on the drain voltage, correct? So I'll not consider that. So remember, it is the R0 of the transistor that is actually coupling the information from the drain to the source side, correct? Because even if we had the current source value depends only on VGS. So it is not coupling any information from the drain side to the source side, right? So which means if I ignore the R0 of the transistors, I have no coupling from the drain side to the source side, which means whatever happens at these two nodes has no bearing to what happens at the source side, right? So which means now I can treat this part in isolation, because I don't care what happens at the drain side, because this will not affect my source. Now if I look at the portion in the yellow box, is that portion symmetric or asymmetric? That is now symmetric. So which means now I can make a statement that Vx is 0. The logic is, I could not make this statement because the circuit was asymmetric, and the asymmetry came about because of this connection happening at the drain side. Now, if I ignore the R0 of the NMOS transistor, the information about the asymmetry is not passed on to the source side. So which means now I can invoke symmetry for this part of the circuit alone and claim that Vx is 0. Again, it is not that difficult to find out. You actually take it as an exercise. You use KCL at the Vx node, and you will find that Vx will be equal to 0. Just one simple equation, you will find that it's equal to 0. But I wanted to give you this, logical explanation. So which means now the circuit is again simplified. So I can redraw the circuit like this. For small signals, my drain is ground. So Vx is ground. This also ground. I have this connection. Here VID by 2 minus VID by 2. So let me label M1, M2, M3, M4. Correct. So now what is the small signal current here? GM VID by 2. Similarly, what can you say about the current here? That is also same. Is it clear? So I'll just mark both of them to be GM VID by 2. So which means the current flowing here is also the same. So if this GM VID by 2 current flows through the transistor M3, what can you say about the current here? So what is the total current that is getting pushed into the output now? GM times VID, 2 times that current. This is the total current getting pushed into the output node. And what is the output resistance now? If I look here, what is the output resistance? Looking down, what is the output resistance? R0 of? Just R0 of M2. Looking up, what is the output resistance? Is that clear? I am looking into the drain side. For the output resistance calculation, my gate is small signal short. So I just have the R0 of the transistor. Same holds good on the top side also. I mean, of course, I've ignored the R0 of the NMOS. That is another thing. So I've already ignored the R0 of the NMOS transistor. So R0 is not there. So this is basically GMVID times R0. I'll not write this R02 because I've ignored the R0 of the NMOS. Yeah, I mean, the only reason to ignore is to make this statement that Vx is 0. Otherwise, I can't make this to be 0. I mean, in the presence of R0, the Vx will not be exactly 0. It will be some non-zero value. So it is not trivial. So just to give a flavor of calculation, I did this. Is this clear?